Thanks to the exciting advancement in machine learning technologies, now AI is more ubiquitous in our daily lives. Because our increasing dependency on these AI systems, it is very important for all the development of AI systems to adhere to responsible AI principles. And explainability is one of such very important principles. Hence, we want to look at what explainability is, and especially for reinforcement learning, where that setting where the intelligent agents are learning by themselves with very little human intervention, explainability is even more important. So to start with, let's first talk about what's the definition of explainability. For the purpose of this talk, and I say for the purpose of this talk because if you look at the literature, you're going to see multiple terminology used to define the concept of explainability. Even though the public setting is the explainability is more popular usage of this terminology in the public setting, in the academia, actually, interpretability is more popular. So just for the sake of the next 18 minutes, let's agree on, for this talk, when we talk about explanation, we focus on what to explain. And when we talk about interpretability, we focus in addition to what to explain, but also how we can explain it to make sure that it's well understood by humans. So based on that, let's look at why it is challenging to tackle or to assess the quality of an explanation. One of the reasons, obviously, is lack of consensus on the definition of explainability. Also, there's a lack of consensus on the metrics that we can use to evaluate explanations. And the quality of explanations itself is very subjective and qualitative, right? So there's really, if you ask different people, some people will understand a certain explanation, but not the others. Why XRL is so important? It goes without saying that ethical concern is a big reason why explainability is important, but also for legal issues that we need to take into account the safety, accountability, and privacy issues of these systems. In addition to operate an AI system, especially for RL systems, explainable systems usually have more transparency, which makes it easier to debug and also easier to maintain of these systems. Last but not least, with better explainability, you can establish trust and confidence in user, which increase the adoption of such system. And I would also like to prompt people to think about the economic reason, right? So having explainability built into your solution can be a differentiator that can generate business benefit. So let's start by looking at how do we categorize these all very different explainability methods. Most XRL methods can find their roots in XAI methodologies. And so let's first look at this very simple taxonomy proposed by Adadi and Berrada. They divide or categorize all the explainability methods along two axes. The first is along the scope of the explanation. So global explainability targeted at the model level. So it's targeted at explain the model itself. However, local explanations focus on specific prediction or decision made by the model. Now, in terms of the timing where the explanation get generated, intrinsic explanations or intrinsic methods are inherently explainable and interpretable, or they're very self-explanatory. For post hoc methods, these are the methods that actually generate the analysis and the explanation after the model has been trained. And so as you can see, that to achieve global explainability is harder, and hence most work focus on local and post hoc methods. Moving along, so build on top of the taxonomy on the XAI methods. Now we look at how we can further classify XRL methods. So this taxonomy published just last year, XRL the current XRL work can be categorized into two camps. One is along the transparent algorithms, and transparent algorithms is nothing new. This is very well understood and well known and commonly used in standard machine learning. So examples like logistic or linear regression, decision tree, these are algos that are very simple, but also very easy to understand. However, for a lot of XRL methods, because they're focusing on mostly deep RL models, these are the explainability does not come as part of the nature. And so most of the XRL methods really focus on very specific tasks that the RL model performs. And I just list a couple categories here without going into further detail. One category of these methods are around learning the representation. And in the RL setting, these are involve learning the state representation, the action, as well as the policies learned by the model. And simultaneous learning basically targeted at learning the policies themselves as well as the explanations at the same time. And hence, explanation is part of the learned components by the model itself. Finally, hierarchical policies or hierarchical learning. These were enable the agents to break down a complex task into subtasks or sub-goals and then achieve them incrementally. On the post hoc explainability method side, they're typically used in perception-related tasks, which means the data involve visual components. And most people most familiar with saliency maps, which indicate which part of the image, input image, will contribute the most to the learned policy. But there's also another category that directly analyze the data gathered from the interaction between the agent and the environment itself. So we'll quickly look at, hopefully we have time to cover two different methods. And first one I want to cover is hierarchical policies. And so these are local, intrinsic, and hierarchical learning methods. So the idea here is very simple. You break down a task into subtasks. And each task in this body of work is described by human instruction. So it's very readily interpretable. And so they form each task as an action or a skill and an item to be involved or manipulated by this skill set. And I'll talk about that with that example on the right. And so the high-level idea is basically you break down these tasks, so at each level, you either leverage the skills that has been learned previously, or you learn a new skill set. On the right-hand side, this is the experiment that I run in the Minecraft game environment setting, where the agent is asked to perform a object manipulation, in essence, manipulating or moving a couple of colored blocks in this virtual environment. And on the top, you can see that the task agent being given is to stack the block, stack two blue blocks together. And this in the beginning looks like very complicated for an agent that hasn't learned any skill. But incrementally, that task has been broken down into first, you need to find a blue block, and second, you need to be able to get that block, and then finally, when you find a second block, you want to stack the first block on top of the second block. So on the horizontal axis at the bottom, you see this is how the learning unfolded. At the bottom of this tree, the blue policies, these are called terminal policies, which are policies that learn very simple tasks or simpler tasks, that is. And that they can involve the direct action like navigating through the room, as well as picking up item or putting down the item. So without going into the detail of the formulation of how they divide up the task into subtasks, I want to point out two very interesting techniques involved in this work. One is they employ the two-phase curriculum learning. So instead of having the agent just learn without any guidance, just sample all the possible actions and try them out, they actually divide the learning into two phases. The first phase is called the basic skill acquisition phase. And so this basically, they sample the task or the policies based on the skills that has already previously learned. And so until the agent is comfortably translating the current level policy into these base policies, once that's done, they move on to the second phase, which is requiring the agent to expand their comfort zone or step out of the comfort zone and learn the new skill. And later we'll see that this actually helps guide the agent learning quite significantly and increase the learning efficiency. The second technique that I deploy is training the stochastic temporal grammar. And again, instead of having these tasks being independent tasks that agents would go and figure out, they actually encourage the agent to learn the relationship between these, especially along the temporal axis, the relationship of these different tasks. And so, for example, before you can stack a block on top of the other block, you have to first find a block. And so this relationship is not prescribed. It's actually learned from the successful previous episodes from the history that agent can learn about these different dependencies between these subtasks together. And again, we're going to later see that this increase the learning efficiency and actually help the agent achieve higher rewards. So the experiment setting is, as I said, they used a Minecraft environment. They first trained the agents along with the block in the small room, so each room, and then the policy of the are trained. And so what they later is they remove the room divider, so now there's a larger room for the agents to navigate and perform tasks. And it's very interesting that with hierarchical policies, the agents are actually able to, the policies that are learned using hierarchical policies are actually generalized much, much better than flat policies where there's no dependencies between these sub-policies. In terms of learning efficiencies, on the top right, you can see that the chart, the orange line is the full model where they deploy the two-phase curriculum learning as well as the stochastic temporal grammar. It not only learn much faster, it also achieve higher rewards. At the bottom shows the effect of the two-phase curriculum learning. Orange line is the one with the curriculum learning, and blue line is without. And so you can see very quickly that the agents are able to exploit the skills that they learn, hence will learn actually much faster overall and also achieve better rewards. In the interest of time, I'll just briefly cover the second method. So the second method take a totally different philosophy here. So cognitive science has taught us or tell us that humans, we actually create these mental models, what we call the causal models, for everything in our environment to help us understand the events that happens and why they happen. And we also leverage what they call counterfactuals, which refers to events and things that did not happen but could have happened under certain scenarios. So having counterfactuals actually helps humans understand events and also predict what's going to happen. And so this approach is basically based on this philosophy. So what this body of work does is actually create this causal model or try to approximate a causal model to explain the behavior of the agents. And so what they did is they extend the structural causal model into what they call the action influence model. So the learning target here is actually what they call the causal equations, which is highlighted as F sub x dot A. So what this is trying to learn is the impact of performing each action on the environment or the state variables themselves. So once this is learned, then there's a causal relationship that can be easily explained by looking at the model itself. And so very quickly, the step to generate these explanations is first to form the model on the right. So this is the action influence graph representation. And the nodes on this graph are all state variables, whereas the edges are the actions performed. So first, this model has to be constructed by humans. So we kind of have a hypothesis how these state variables interact with one another via these actions gets performed. And the second step would be to actually learn the quantity of the actual impact a certain action on all these different environment variables. And they use regression learners to perform this step to learn the quantity. And finally, with the structure and the quantity involved, now it's time to extract the explanation from the graph. And so by that, we'll follow the causal chain, which basically are the shaded nodes here, to explain why agents follow certain policies because they cause these impact in these environment variables. Now, interestingly, with this graph, it's also very easy to reason counterfactually because, as you can see, the alternative action here is the AB. It has its own causal chain, and so you can compare the difference between two causal chains and know the impact of and the reason why the agent didn't take an alternative action because it doesn't lead to a higher reward. So this is an approach that depends on the causal relationship. So very quickly, their experiment shows that indeed they try this on 5 open RL environment as well as the StarCraft 2 environment. And what they found is for the problems or the environment that has clear causal relationship, this model actually works better, and this is not surprising. Hence, in the table, you can see the highlighted row at the bottom. This is the StarCraft, where this approach is really, really effective because it's a strategic game, and every action has a causal relationship to the outcome of the result, whereas the other environment that's more random, this approach doesn't perform as well. Another interesting finding that they have is that for learning these causal equations, the quantity of performing the impact of an action on the environment variable is actually using linear learner is very effective, and using something like a MLP multi-level perceptron is actually doesn't give you anything better. So that's an interesting. Now, what's worth pointing out is this work is very different from other work in terms of they also perform the empirical evaluation via human study. And so the two hypotheses that they tested, one is whether having a causal model will help understanding, increase the quality of the understanding in users, and it's a clear yes. The second point is very interesting when they say, well, if you have a well-explained model, does that increase the confidence or the trust that user have for the system? And the result they find is, yes, it might help a little bit, but it's not statistically significant enough for them to say an absolute yes. So that's just a very interesting observation. So I would just like to leave this everyone with these ideas, and hopefully this will inspire you to think about explainability and interpretability in your next RL or even broader AI project, because explainability matters and responsible AI development matters. Thank you for your attention.
Thank you so